Question on Hooke's law. So being asked to sketch a graph to show that a spring does obey Hooke's law as it's stretched. In order to do that, you need to be able to know what Hooke's law is. So Hooke's law is F is proportional to X, or rather F is equal to Kx. So because we have a directly proportional relationship, that means that we are looking for a straight line that passes through the origin. So that's the first thing you need to be aware of. The other thing you need to be aware of is how we label our axes, as we are told to in the question, and that means that you need to label this axis with force and that you need to label this axis with the extension. The way the marks are awarded here is you have 1 mark for labeling the axes, 1 mark for a straight line, and 1 mark for it passing through the origin. Bringing in some work on forces now. So the object is initially at rest, it's then pulled down and released, and the diagram 2 is showing us the forces acting as it is released. Determine the magnitude and direction of the resultant force. So remember, a resultant force is a single force that replaces the 2 that are acting. So what we're looking for here is we have got 3.2 acting upwards, but we have got 2 acting in the opposite direction. Remember, forces are vectors, and therefore that resultant force has a value of 1.2. Which direction is that happening? Well, you can see that the force upwards is greater than the force downwards, and therefore it is going to be in the upwards direction. Calculate the acceleration of the object at the instant it is released. So we are now going to need to go to our formula sheet, and we're looking for force is mass times acceleration. The thing to remember here is that this force here should be a resultant. So that's where we need our answer to our previous question. So if we rearrange that, we know that acceleration is force divided by mass. The resultant force from our previous question was 1.2. Our mass is 0.2, and therefore 1.2 divided by 0.2 gives us an acceleration of 6 meters per second squared. If you were to get the answer to part 1 incorrect, but you were to use it correctly here, you would of course get ECF, which is error carried forward. So make sure you show your working to show that you know that the force from part 1 should be used in this way in this part of the calculation. Now we're asked to explain how the acceleration of the object is going to change from the moment it's released until it returns to its initial resting position. So you're being asked to refer to the forces acting on the object in your answer. So we've got the force upwards provided by the spring, and we have the weight downwards acting against that. So bear in mind, as the spring is released, if we look back at our diagram, we can see that the spring extension has actually decreased. Okay, so once the spring is released, we have got a decrease in the extension of the spring. Okay, what that means is if the spring's extension is decreasing, then the force from the spring is also going to decrease. So the force from the spring is going to decrease, or you can simply refer to the upwards force is going to decrease. But we know that the weight is going to remain exactly the same because the weight isn't changing. So the weight remains the same, and therefore if we have the same size force downwards but we have reduced the force upwards, what that means is that our resultant force is also going to decrease. And that decrease is going to happen to 0, at which point there will be no acceleration.